This is the video on light. So there are codes in this video. One will be a written code that will pop up on the screen. The other will be a verbal code said by myself. You will need both those codes in order to move on with any of those homework assignments. All right. So when you're looking at this video or looking at the slides that go along with this video, you'll notice that some of the text is in green. That's the important stuff. It'll make it nice so you can bullet point all the important ideas. The rest is just good information to have. So this is the weekly review written code. I would recommend you write this down somewhere. So light is a wave, right? Now, we're just going to jump right in and talk about the refraction of light. Remember, the refraction of light is like the bending, or refraction of any wave is the bending of that wave when it crosses a medium. Now, it's really apparent with light because, like, if you put this like a glass block down, you can definitely tell that there is a definite change in medium right there, and you can see that that light is going to bend. So the refraction of light is the bending of light as it passes from one transparent substance into another. And this is why we have lenses, magnifying glasses, prisms, rainbows, telescopes, microscopes, just using this property of waves. So this is how Isaac Newton was the one that found that white light consists of all other visible colors. So he identified Roy G. Biv, red, orange, yellow, blue, indigo, and violet that make up the visible spectrum. And that's because the refraction of light and those different colors refract at those different angles. So that was just the beginning, though. In 1800, William Herschel recreated Newton's prism experiment, except he used thermometers to measure the heating of the different colors. So he noticed that red light produced more heat. Now, one day when he was doing this, the sun moved across the sky, and one of the thermometers was just outside of the red light. Now, the temperature did go up. Now, this led him to discover the electromagnetic waves, like the electromagnetic spectrum. Now, electromagnetic waves, like light, do not require a medium to propagate. They're not a mechanical wave. This means that the electromagnetic waves can travel not only through air and solid materials, but also through the vacuum of space. Now, the electromagnetic spectrum is the range of all types of electromagnetic radiation. So radiation is energy that travels and spreads out as it goes, and light waves are forms of moving energy made of particles called photons. So you can see here, this is that famous experiment that William Herschel did to discover that there was something else beyond that visible spectrum. And you can see that that visible light isn't that much of the spectrum that we see, like, or the whole electromagnetic spectrum. It's a very narrow band, and we've got gamma rays, X-rays, ultraviolet or visible light, infrared, and radio waves. Now, we take advantage of this to send information, but we do not see a very large part of that electromagnetic spectrum. And if you read some of the text there, like William Herschel also discovered the planet Uranus in 1781. Just kind of a fun fact, he named it George after King George. Eventually, they changed the name, but as a little consolation, all the moons of Uranus are named after Shakespeare characters. All right. Now, why is glass clear? So it all has to do with what color is. Now, what happens is this happens on an atomic level. Now, just to shorten it, like light waves are going to come in, they're going to interact with those atoms, right? So the electrons can first absorb some of that light that hits the atom and molecule. The electrons, which absorb the light, then will emit or give out some light. It gets a little more complicated here. But essentially what happens is that if you've got white light and everything reflects, well, then your brain just interprets it as red light, or sorry, white light. Now, if you're looking at something that has the color red, what that object is going to do is it's going to absorb all the other colors except for red. Red is going to get reflected back. Now, glass requires much more energy to be excited, which means those photons of visible light travel through glass instead of being absorbed or reflected, making glass appear transparent, right? That's why light seems to travel through. Now, glasses are really good at absorbing ultraviolet light, and that's why it's hard to get sunburn indoors or a car, right? Because window blocks those harmful ultraviolet rays. It's like the equivalent of wearing 30 SPF. So it's not like perfect, but it does protect you from those ultraviolet rays. All right. Like our body interacts with those electromagnetic waves, those visible lights, as like rods and cones. right? Or sorry, rods or night vision, but cones interact with those color waves. And we have three different types of cones, and that allows us to see all the different shades. Now, somebody that has dichromats or two cones are called dichromats. Those are like colorblind. So you've probably, if you've been to the eye doctor, you might have seen these tests. What they're testing for is some sort of color blindness, like you're missing one of those cones and you just can't see as many shades. Now, on the other spectrum, there's something called tetrachromats, which are believed to have 4 different types of cones, and they can see different shades. They can see more shades than the average person with 3 types of cones. All right. Could someone drive so fast that they never encounter a red light? So that brings us to the Doppler effect. So remember, the Doppler effect is an increase or decrease in the frequency of sound, light, or other waves as the source and observer move toward or away from each other. The Doppler also affects light emitted by other bodies, or like in space, right? It also does affect light. So if a body in space is blue shifted, its light waves are compacted, and that object would be coming toward the observer. And now if it's red shifted, the light waves are spread apart and it's traveling away from the observer. So you can see in this picture up here, like you've got a light source. If it's going towards somebody, well, it's going to compress those waves. And let me just show the color. What it's going to do is it's going to compress those waves, and it's going to be shift down towards the blue end of the spectrum. But if that object is moving away, then it's going to shift towards the red end of the spectrum. You're going to see it's a little more red. Now, this is how astronomers tell if stars or galaxies are moving toward or away from us. It's actually how they discovered that the universe is expanding, and that expansion is accelerating. Now, theoretically, if you were to drive fast enough towards a red light at a traffic light, that would appear green. So you can see that what you do is you would shift that red light, blue shift it down to the green side, right? Now, in order to do that, you'd have to be driving incredibly fast. So essentially like 18.3% the speed of light, right? So that's fast enough to travel around the world in about a second. So don't blame me for like getting a ticket saying, well, oh, if I drove fast enough, I could see a green light. You'd have to be driving about 20% the speed of light. But this is how radar guns work. What they do is they emit a known frequency of like a radio wave, and then based on that object, whether like how fast it's coming towards them, it'll compact those waves, and the radar gun can image that or like calculate it. All right, and it's best just to drive safely, right? That's always the little go-to here. All right. What is Snell's window? So in order to understand like Snell's window, we did this lab. I call it Snellulator. It's all about Snell's law. So you can see we've got a refraction tank, and we're shining lasers from water to air, air to water. That brings us to Snell's law. So Snell's law is named after Willibrord Snellius. Snell's law is a formula used to describe the relationship between the angles of incident and refraction when referring to light or other waves passing through a boundary between 2 different media. So the angle of incident is the angle between the incident ray and the normal. So the normal is a line going, now normal in math means perpendicular. So what that means is that it's going like this line, this normal, this pink line right here is perpendicular to that medium change. That's what we call the normal. Now the angle of incident, that angle is basically the angle that light wave is going to enter that medium change. And the angle of refraction is the angle that the refracted ray makes with the normal line. So basically, what angle is it going to leave that medium change? Now, the index of refraction is the variable n. So if you look up top, that is Snell's law. It's got the index of refraction and of the angle of the incident multiplied by the sine of the angle of incident, and on the other side you've got the refracted side. It does get a little complicated there, but the index of refraction right here, this is the equation for that. We don't really use it too much to calculate it, at least in this class, but you can see that it's equal to the velocity of light in a vacuum divided by the velocity of light in the medium. It's basically a ratio that says how fast that light is traveling through that material, comparing it to the fastest it's going to go in the vacuum. The higher the number, the slower it's going. So you can see here's the indices of refraction. You've got vacuum, it's going to be 1 exactly. And air, well, 1.0003. Air doesn't slow down the speed of light that much. Now, in that lab, we tested air and water. Water is 1.33. Now, oil and glass, they're pretty close. So that's why if you've got a jar of like vegetable oil and you put glass in it, it's kind of hard to find it because water doesn't, or that light won't really bend that much when going between those different media. And diamond, incredibly high index of refraction, 2.41. Essentially, it slows the speed of light down to about 40%. So if we're looking at Snell's law, how to tell which way the light will bend. So you can see there's a little diagram here saying which way the light will bend. If going from a faster to a slower medium, the light will bend towards the normal. If going from a slower to a faster medium, the light will bend away from the normal. Now, here's how I like to imagine it, right? So you can see up here, like a lawnmower, right? So think about going from concrete to grass or grass to concrete. If you're going in at an angle, if you're on the concrete, you're pushing that lawnmower, well, and you're going in at an angle, well, that front, one of those front tires is going to slow down first, causing you to turn that lawnmower. And if you're going the other direction, if you're going from grass to concrete, you're going from a slower to a faster medium, well, that front, one of those front tires is going to speed up before the rest of the mower, and it's going to cause you to turn away from the normal. So this is exactly what's happening with the light rays when going from one media to the different media. What's happening is it's basically part of that wave is turning before the other part of the wave. All right, so that brings us to a special case. And well, oh, sorry, not the special case yet. This is why, like, if you look at something in the water, it's not actually where it is. Like if you're spearing a fish, right, you always want to aim below the fish because the refraction of light makes the fish appear closer to the surface than they are. The distance that you aim depends on how far away you are from the fish and how deep the fish is in the water. But essentially, if you look at this diagram up here, that fish, you can see the light that hits off the fish, and it's going to go to this medium change, going from water to air. It's going to speed up, and it's going to refract away from the normal, and it's going to hit your eyes. And your brain just says, well, light goes fast, light goes straight. So you interpret it just above where it actually is. So in spear fishing, or if you're getting some out of the water, you want to aim below where you are actually seeing it. And that's Snell's law. Now, there is a special case, though, the critical angle. The critical angle is when the light rays or light waves are passing through a slower medium to the surface of a faster medium, or dense to less dense medium. Well, then those rays are going to no longer be refracted, but totally internally reflected. This is how diamonds are cut. They are cut to maximize total internal reflection. So you can see here, if I'm going from a slower to a faster, this only happens with slower to faster, there's going to be an angle with the normal at which the angle of refraction is 90 degrees. That's the critical angle. Anything more than that, and it's going to reflect off that medium change. So you can see here, that's how diamonds are cut, right? Diamonds are cut to take in that light, that visible light, and you can see it refracts, then reflects, and it goes back out. So it basically takes that light, goes in, and it's colorful because you do have some of that prism effect when the light gets refracted out of the diamond. So a lot of like math and trigonometry and physics go into cutting these diamonds. So that brings us to Snell's window. It's just an interesting phenomenon where if you're underwater, you're looking up, you'll only be able to see a small window, and there is like a 96 degree or 97, somewhere in there, a window that you'll be able to see above the surface, but you're actually seeing everything above the horizon because of that light getting refracted down into the water. Everything beyond that is going to be reflected. So you can see it's a perfect view of that critical angle. Like there's a definite line between getting refracted and then getting completely internally reflected. This is how fiber optic cables work. So essentially what it is there's a, like you have this dense medium in the center and then a less dense on the outside, and basically if you go in at the correct angle greater than that critical angle, it's going to continually internally reflect. So light travels down that fiber optic cable by bouncing off the walls of the cable repeatedly. Each light particle, the photon, bounces down the pipe with continued internal mirror-like reflection. So one strand can make as many as 25,000 telephone calls, and one fiber optic cable can easily carry, several million calls. A copper wire can only make one. So you can see this picture of like these switching boards, because you had to basically connect every phone to every other phone to send that information. But when we're using fiber optics, well, it's just light bouncing off those the internal fiber optic cable, because it takes advantage of that critical angle. So I'll go ahead at this time, give you the verbal code. The verbal code is 506. I say that again, the verbal code is 506. So this is sort of how PRISM works. Different colors of light travel at different speeds inside the glass, right? So it does have a little dependence on wavelength, because the shorter the wavelength, it's going to interact with more atoms and it's going to slow down more, right? Longer wavelengths like red, well, they're longer, so they're not going to interact with as many as that the shorter waves like violet, right? They get refracted at different amounts. Violet has the slowest speed and gets refracted the most. Red has the fastest speed, gets refracted the least. I mean, that's how prisms work, and that's what Newton did in his experiment. So what is a rainbow, right? A rainbow is just a result of refraction and reflection inside raindrops. So after it rains, there's going to be moisture in there, these raindrops. Well, the sunlight, if the sun's behind you, it's going to, you can see it refracts inside, then reflects, reflects, then refracts. And because those different wavelengths travel at different speeds through the medium, it's going to separate those, and what you're going to do is see a rainbow, right? Rainbows can be full circles. Technically, they are full circles, but since they're observed from the ground, they look like they're bowing, like an arch, right? Yeah, no one ever sees the same rainbow. Even if you're standing right next to someone, it will be different light from different water droplets. So why is the sky blue, right? Light scattering, right? The blue color of the sky is caused by scattering of sunlight off the molecules of the atmosphere. This scattering, called Rayleigh scattering, is more effective at short wavelengths, so the blue end of the visible spectrum. Therefore, the light scattered down to the Earth at a large angle with respect to the direction of the sun's light is predominantly in the blue end of the spectrum. So within the visible range of light, red light waves are scattered the least by atmospheric gas molecules because they have the longer wavelengths. So at sunrise and sunset, when the sunlight travels along the path through the atmosphere to reach our eyes, the blue light has been mostly removed, leaving mostly red and yellow light remaining, red, orange, and yellow. Right? This causes a really interesting phenomenon to happen during a total lunar eclipse. So just thinking about where does space begin? We called it the Kármán line. It's basically once you get past the point of that blue light scattering and you're seeing the space, that's sort of what we determined as like the beginning of space. So there's lots of different ways you can do that, but that's just where we like have designated that, where blue lights just stop scattering and then you can see the stars. And all right, why does the moon turn red during a total lunar eclipse? So if you've ever seen a lunar eclipse, you can see a little graphic up here. Well, what's happening is the Earth's shadow is going over the moon. It can be seen just as the whole moon is about to be eclipsed, the moon turns red briefly. So you can see it turn red. What's happening is this is due to the scattering through Earth's atmosphere. The shorter wavelengths are scattered or absorbed the red light that makes it through. Essentially, it's a reflection of every sunset and sunrise on planet Earth at that moment. So what happens is that we talked about the medium change. So that light is going from vacuum into air, which it does slow down a little bit, right? Remember, the index of refraction are close to 1, but not the same. So what's happening is it travels the atmosphere. Those smaller wavelengths like purple and blue, they get scattered, right? But that red light and the orange light make it through, and they get refracted down towards the moon. And that's why the moon is going to look a little bit red during a total lunar eclipse. So once again, there is too much unknown in the universe to take a break from learning. Get out there and question everything.